Welcome, everyone. This is the 22nd Climate Intervention Virtual Symposium. We have three speakers today. I'm waiting for the other two speakers to come, but I I hope they are going to show up. Otherwise, we're going to have a short symposium today. The first speaker is Miranda Hack. She's a third-year PhD student at the Columbia University. She recently published a paper she's going to talk about. Um, as we know, we have 20 minutes for the talk and then 10 minutes after each talk for Q&A. Miranda, you can share your screen and um, present
Okay,
your.
cool. I will go ahead and share my screen then. And just to make sure everyone can hear me. Okay, can everyone see that? Let me make sure I can see it. Okay, cool. All right. I will get started. Hi,
Oh,
everyone.
sorry, Miranda, I was muted. No, I cannot see. At least I cannot see your screen.
Oh no. Okay, let me try again. Share. How about now?
Yes.
Okay. Still good?
No, the moment you press the
Oh,
button play,
okay.
okay, now we can see it.
Good. Okay, cool. Sorry about that. Hi everyone. I'm Miranda. I am a third year in Faye McNeil's group at Columbia University in the chemical engineering department. Today I'm going to be talking about our paper in collaboration with a few other Columbia faculty, Dan Steingart, also in the Chemie, and Gernot Wagner in the Columbia Business School. And our most recent paper is entitled Engineering and Logistical Concerns Add Practical Limitations to Stratospheric Aerosol Injection Strategies. Um, so I'm going to start out by talking about sort of what we know, which is that we have a decent idea of what an ideal SAI deployment scenario might look like in terms of risk. So we know that it's ideal to minimize the two sort of well understood or better understood risks, which are ozone-related heterogeneous chemistry as well as stratospheric heating, either of long wave IR radiation or shortwave. And so this first risk of ozone-related heterogeneous chemistry, you can minimize either by selecting chemically favorable species, so that is species that tend not to uptake halogen-containing reservoir gases that can lead to the production of ozone-destructive chlorine radicals, or minimize in addition, the partitioning of a reactive NOx species in the particle phase to sort of limit this heterogeneous surface chemistry-related ozone depletion. In addition, the choice of strong shortwave scatterers can also minimize indirectly the amount of aerosol you need to put in the stratosphere for a given radiative forcing target. So that's a sort of indirect way to go about limiting this risk. The same is true for stratospheric heating. So a lot of non-absorbing species in the IR have been proposed to sort of lower this risk in comparison to sulfate. But in addition to this, even the use of stronger shortwave scatterers can indirectly limit this risk by lowering the total amount of mass that's needed to achieve a shortwave forcing target. In addition to this, we also know that there are some parameters that ideally, in an ideal SAI deployment scenario, you would maximize. So one of those being stratospheric aerosol optical density and ensuring that it's somewhat uniform. And this predominantly has to do with the latitude that you inject at. This has been very, very well researched. But so the idea of tropical injections or injections at the equator, although you have a lot of lifetime benefits with the upwelling of the BDC, this ultimately leads to a concentration of stratospheric warming around those tropics, as well as tropical overcooling, while the inverse is true of something like polar injections. We also consider in this paper what we call a decentralized scenario, which is a scenario that might take place if injections happen sort of without some sort of overarching governance, or in the case where they happen on the basis of population density. So in that case, that might look something like injections that tend to be concentrated in the northern hemisphere where 90% of populations are. And in that case, that's also sort of a non-ideal injection scenario when it comes to aerosol optical density evenness, because you have this concentration that's really concentrated in one hemisphere that leads to impacts on things like the intertropical convergence zone. So injection latitude is really important and is really a key deployment parameter to optimize. That's why the people at Glens have been, in particular, working so hard to look at this sort of multi-latitude injection scenario in which you inject at multiple mid-latitudes to sort of achieve this uniform aerosol optical density. But things like lifetime and efficacy of the aerosol burden are also quite important when you're considering what an ideal SAI deployment scenario might look like. So parameters like the altitude of injection can have impacts on lifetime, as well as latitude, obviously, matching up the season so that you match peak SAODs with peak sunlight, and ensuring that you're operating at magnitudes that don't lead to massive microphysical constraints. Also can all sort of interplay to sort of impact how ideal your lifetime and the efficacy of your aerosol burden is. So the reason I talk about this is because we have an idea of this sort of idealized deployment scenario, and this is sort of infinitely testable in our modeling setup or in someone who's running a GCM. You can sort of probe that design space really to a really broad degree. But the question we really wanted to ask was sort of what are the practical limitations to achieving this idealized SAI scenario? So we sort of split this up into two sections, one being human level constraints. So these are things like supply chains. How feasible is it actually that you can use a material with these sort of idealized properties, given current supply chains, as well as governance, which I sort of discussed in terms of injection latitude. So how are those sort of deployment parameters that you would like to optimize actually optimizable in a realistic governance scenario, as well as technical constraints. So predominantly on that front, I will be talking about the dispersibility of solid aerosols, and how that might influence things like size distributions and shortwave forcing efficiencies. So basically, the focus of this paper was looking at, we have all these knobs to turn, right? In past literature, we've done, I think, a really great job of turning all of these knobs and looking at how, what the optimal position for them might be. But I think now it's really important that we start to ask the questions of how might realistic constraints force us out of those optimal situations, and what are the risk implications of that. So even if we know that this material, X material, is great, can we actually use that? Is that a feasible scenario? And what might that mean for what our actual options are? So with that said, I'm going to talk a little bit mostly about supply chains and dispersibility. So sort of taking it back to Econ 101. One of the questions we wanted to ask was, with SAI size demands potentially inflating demand, what supply chains of the list of materials that's been proposed might these demands pose a threat to? And how would those supply chains potentially respond? So we do this in part by estimating a quantity called the price elasticity of demand, which is the percent change in the quantity of something that's demanded for a given percent change in price. So if there's demand pull inflation that inflates the price of a given material, how does demand respond? And are there potentially like flexibilities in that demand that means that prices won't be skyrocketing with big increases in demand? So we do this using historical mineral data for raw materials for a lot of the candidates that have been proposed. And we use a very simple log-log regression model to take a look at this PED for this data, which is this first quantity. And we also account for things like changes in supply as well as general economic status in this model. What we find is that there are several materials that potentially have concerns with demand pull inflation. That is to say, their potential SAI-induced demand is relatively significant. So we look at a relatively moderate SAI scenario. This is one that halves the rate of warming, and we look at the burden that's required in the 15th year of that scenario. And we take that as a fraction of the production in the year 2023. So how much would production have to increase fractionally to increase that demand is this number here. And we see that particularly for candidates like zirconia, titania, and diamond, this represents a pretty significant fractional demand increase. So those are the candidates predominantly that concerns with demand pull inflation arise with, because this potential SAI-induced demand is significant. We also find that demand for minerals is highly inelastic. So this PED number that we quantify is much less than the absolute value of 1. So an elastic material has a PED of -1, and a completely inelastic material tends to be around 0. For luxury goods, so like looking at diamond, it can be a little bit greater than 0. But yeah, most of these are significantly closer to 0 than they are to -1. So they're highly inelastic quantities. And the reason that we care about this has to do with equilibrium price. So here I have pictured lime as an example, which is the raw material for calcium carbonate. So we have supply in black, and this is the supply curve, and we have the original demand curve in dark blue. And where this black and dark blue curve intersect is the original equilibrium price. As you inflate the demand, so in an SAI scenario, say you inflate the demand 10%, you shift that demand curve to the right, and you have a pretty significant change in equilibrium price. So it goes from, say, 125 to something like 600, which is a pretty massive increase because this good is so inelastic. But if I change that elasticity, let's say I change it by a factor of 10, you can see that for the same increase in demand, the change in equilibrium price is much less significant. So even marginal elasticity can be really beneficial when you have these really significant demand increases. So this is all really important stuff that has to be considered when we're thinking about what candidates are actually feasible for relatively significant SAI strategies. Next, I kind of want to shift my focus to technical constraints, and I want to talk about the dispersibility of mineral, specifically solid mineral aerosols. So one of the reasons that mineral aerosols have been proposed is that they tend to backscatter more shortwave, so more sunlight, a lot more efficiently than sulfate aerosol per mass. So this is shortwave radiative forcing in a clear sky atmosphere for monodispersed burdens of 1 teragram of each of these materials. Basically, you can see that particularly for submicron radii, these solid candidates have a much higher or larger shortwave forcing efficiency. But this scattering advantage is really lost as the solids approach, say, 0.5 micron in diameter, and sulfate actually begins to scatter better as you approach these larger size parameters. So this is something that's pretty significant because in addition to these mineral candidates also tending to absorb less in the long wave than sulfate, which is part of why they were proposed, this shortwave efficiency is also of concern. In particular, because while this efficiency is maintained in this really small 200 to 300 nanometer radius region, dispersing submicron particles in this region is notoriously difficult. So this is a Geldart plot of what Geldart in, I think, the 20th century grouped nanomaterials and micro-sized materials powders into a bunch of different groups based on their particle size and their density difference of the material that you are fluidizing and the fluid that you are fluidizing it in. And so he has these 3 groups up here, which are all readily fluidizable, and at very small particle sizes, this submicron range is even off the axis of this plot. You have Geldart's group C of cohesive materials, or quote unquote hard to fluidize materials. So it's clear that this is something that is a challenge, particularly for the types of materials that yield this shortwave scattering efficiency over sulfate. So in particular, we were concerned with the ability to disperse solid aerosols in this submicron form. And we were particularly interested in dry dispersion methods. So that is not necessarily just suspending the solid in water and nebulizing and drying it, but how might you fluidize it in order to, one, preserve properties that might be altered by making a suspension, and so surface properties can be changed in that sort of dispersion setup, and 2, also it seemed really appealing to not have to consider lofting some sort of solute or material to disperse them in. So we look at this dry dispersion scheme, which is based off of a lot of dry dispersion solid aerosol literature. But first, you undergo some sort of particle milling step to break up larger agglomerates before you fluidize the material and ultimately inject it using some sort of spray nozzle. And this ultimately is proposed to break up these agglomerates, but we can even see the presence of these agglomerates in sort of lab-based particle generation techniques. So this is something our group has been working on for a while. And this is another paper that's recently out, but we have developed solid aerosol generations in lab. In this case, we're using a subwoofer-based method that uses a lot of the techniques shown here, one being particle milling. So we use carbon steel balls to sort of mill a nanopowder, and then we also fluidize it just using a nitrogen flow while the subwoofer sort of mechanically and acoustically agitates it. So I have a video here that you should be able to see, but even just like on a macro scale, it's quite clear. This is calcium carbonate pictured. That calcium carbonate likes to clump up, like it likes to form these little balls. And we're actually, I think, using washers here, not carbon steel balls. But when you add those carbon steel balls, breakup becomes a lot more plausible. But even so, when we measure what's coming out of this generator with two separate particle sizing instruments, we see the presence of large aggregates. So we measure them with a scanning mobility particle sizer, which measures less than roughly like 800 nanometers in diameter, and an aerodynamic particle sizer, which is greater than half a micron in diameter. And the bulk of the surface area here comes from particles that are much larger. Or measured by this bigger instrument, so greater than half a micron, even though the primary particles that we're using here are roughly 300 nanometers in diameter. And the number mode diameters that we get out of this really represent aggregates, mass equivalent of more than 100 monomers, or more than 100 of these primary particles. So that's pretty significant. So with that in mind, we think it's pretty important that we understand the shortwave properties of these aggregates and why it's important to break them up. So we model shortwave properties of these aggregates. We do this at a bunch of fractal dimensions. Here I've shown the fractal dimension of 2. But as you increase the number of monomers across all candidates, the shortwave forcing efficiency drops off pretty rapidly. And here in blue, I have pictured the shortwave forcing efficiency of a roughly optimally sized sulfate aerosol. So you can see that for these large aggregates, the shortwave efficacy is lowered pretty significantly. And in addition to this, these aggregates are pretty big, so they're going to settle much faster. And you're going to need more aerosol for a given forcing target, which means more injection rates, more surface area for ozone chemistry or ozone depleting chemistry to occur on, as well as more mass with somewhat unprobed long wave optical properties to potentially impact long wave absorption. So those types of risks seem more acute with these aggregates than with the scenario that has been modeled, which is these sort of optimal monomers. So with that in mind, we really were like, okay, what is the best way to break up these monomers? And we're looking at if doing so using a dry dispersion system is possible. So I want to talk about this third step in our sort of explored dispersal scheme and talk about modeling agglomerate breakup likelihood in a choked convergent barrel nozzle. So how this works is a nozzle, as I'm sure everyone here knows, accelerates a gas by constricting it. And in this case, our gas is moving faster than our particle. So the velocity differential between the gas and the particle imparts a drag force on the particle. And in theory, this drag force opposes any cohesive intermolecular forces and acts to break up that agglomerate. So in this case, we model intermolecular forces with van der Waals forces from Lifshitz theory. In reality, there's probably more at play here, given electrostatics, hydrogen bonding, any relative humidity effects, etc. But in this case, we're just looking at van der Waals forces. And we compare the ratio of these two forces in a flow field along the nozzle using a modified Weber number, which is just the ratio of these two forces. And basically what we say is that if this Weber number is less than 1, agglomerate breakup is not possible at that point because the cohesive forces outweigh any sort of forces that might pull them apart. So we do this at a variety of conditions. On the left here, we're looking at really, really low mass fractions of solid so that this flow of the solid doesn't impede the flow of the gas at all in a variety of gas inlet conditions. So I'll take a representative curve in green here. This is a pretty compressed gas, but what you can see is that the gas is accelerating to a dimensionless distance of 0.5. This is where the throat is reached. So this is the maximum speed. This is the choking velocity of the gas. And then the particle is accelerating along with it. But Weber numbers are maximized here because this is the maximum velocity differential between the particle and the gas. And then as the flow continues to be choked throughout the barrel of the nozzle, the particle sort of catches up. So that's why you have these shapes of the curves. But basically what we see is that using the gas that's available in the stratosphere, so that is a very cold and a very low density gas, it's very hard to impart significant drag because one, it's not very dense, and two, speeds of sound at low temperatures are much lower than at room temperatures. So a compressed gas will be needed. In addition, we also take this compressed condition and look at varying mass fractions of solid. So if you increase that mass fraction of solid, how might that impact the flow of the gas and the ability to impart drag again on this agglomerate? And basically, we see that as you would expect, having more solid in the flow limits the ability of the gas to accelerate and limits the drag that can be imparted on that solid. So why do we care about this? Mostly because we sought out to look at this dispersion system because it might mean that we don't have to bring up a lot of heavy dispersal materials to the stratosphere. What it looks like is even with this quote unquote dry dispersion, this best case scenario in yellow still requires something like a 35-to-1 gas to solid mass ratio, which is really significant. So there are definitely payload constraints there that should be considered. And I think this also really just calls for if solids are to be considered, and it's something that is being modeled, really a lot of creativity on this front of how might we ensure that aggregates aren't formed and that sort of this constraint is overcome. So concluding thoughts, basically just to summarize everything I've talked about today, the lowest risk SAI strategy has ultimately really three requirements. So one is chemically and radiatively favorable materials, which might be limited by earth abundance and inelastic mineral supply chains. Two, it requires that they be dispersed in near optimal particle size distributions, which might be technically challenging to achieve at scale, particularly for dry dispersion methods, which might add payload constraints. In addition to this, microphysical constraints post-dispersal, such as in-plume coagulation, add really additional uncertainties given what we know about these submicron solids' desire to sort of form these aggregates. And three, the lowest risk SAI strategy also requires deployment with optimal deployment parameters. That is to say, some sort of coordinated governance or the absence of like governance that interferes with the ability to achieve those optimal parameters is really significant. This work was funded by the Simons Foundation. Thanks to everyone who collaborated, and that is really all I have for today. So thank you.
Thank you, Miranda. This was really useful considering the growing interest in using solid materials as an alternative to sulfate. I have some questions, but I want to see if there's someone else since we have only a few minutes for questions. Um, I don't see anything in the chat. Um, so you show that plot for the radiative forcing efficiency for different compounds. I think it was slide 7. Uh,
Yes. Oh, this one.
7,
I got
yes.
you. This
Which is
one. Yeah.
actually related. So my question is also related to slide 17. Um, when you calculate these radiative efficiency, I probably missed that. What injection scenario did you consider? Is that the same amount injected for each species or the most efficient strategy? Um,
Yeah. So this is per teragram of burden. So I put basically just like a uniform layer of a given mass of each species, if that makes sense. So this is like a not a model that necessarily accounts for differences in settling, but or difference, yeah. So like obviously solids are denser, they're going to settle out faster. So they might require a higher injection rate to achieve the same burden. But this is only for the same actual loading in the stratosphere, if that makes sense.
Okay, so you excluding the effects of microphysics if we are
Yes.
interested. Okay,
Yes.
okay. Okay. There is a question from Mike. Mike, you can unmute yourself.
Um, Thank you. So this chart basically shows that these minerals would be maybe, what, twice the scattering efficiency or so of sulfate. But then there's an awful lot of problems in dispersing or something like that.
Mhm.
So I guess I mean, is it really worth going after the mineral ones compared to sulfate, or is putting out SO2 just so much easier that it would be easier to do at least first and figure out, alternatives over time?
Yeah, I think that's a great question. I think that's really the heart of what we're trying to get at here. And I think particularly given the long wave properties of some of these materials and their ability to minimize um, that sort of risk, I do think there certainly are benefits to exploring how that dispersion limitation might be overcome. Um, and I also think the long wave properties for these types of aggregates still need to be probed. Um, but I think there's a lot of open questions there. And I don't think the fact that they're difficult to disperse is necessarily like a conversation ender. But I do think it requires perhaps a little bit more creativity in how that might be overcome.
Thanks.
We have time for one more question. Tyler?
Thanks, Miranda, for your presentation. Would you repeat your conclusion on the price elasticity of demand analysis? I'm sorry, I missed it. And I was just curious, did you look at the size of the market relative to what the expected size of the new customer would be?
Yes.
Um,
Okay.
and then I, yeah, yeah.
Okay. Yes. So I think the size of the market, as we've presented it here, is the production in the year 2023, and then we look at the percent of that production that an increase in demand for SAI would represent. So,
Okay.
and this is again a very moderate SAI scenario. So it's having the rate of warming. So the 15th year of having the rate of warming, I think an RCP 6 um, requires a 40% increase in production from the 2023 value for zirconia. Does that make sense?
Yes, yeah, thank you. Thanks.
Okay, thank you, Miranda. I think we should move to the next speaker, uh,
Thank
Morgan Goodwin. You want to try to share your screen? Okay.
Yes.
Morgan
Thank you.
Goodwin is the executive director and project lead of Planetary Sunshade Foundation. As the name says, is an organization dedicated to advancing the concept of planetary sunshade. Um, yeah, the floor is yours.
So, thank you, Ilaria, and thank you all for being here. I am excited to introduce the work that we are doing on the planetary sunshade concept. And so I'm going to get right into it. We had a slight mix-up on the time this morning. So Jeff Overbeek, my our technical lead and my co-presenter, is not with us yet. Hopefully he'll join us for the Q&A. But we are a nonprofit research organization working to advance the concept of space-based reflectors. And we serve both a research role and also a convening role. And so we are the sort of the hub for all the planetary sunshade efforts going on. Just a word about myself. I come from a climate policy background. I've spent the last 20 years working on renewable energy, fossil fuel, stopping fossil fuel infrastructure projects, and working kind of in the mainstream environmental movement. And I got pulled into this work because of I think like many of us, the realization that those efforts are necessary but insufficient. And the Planetary Sunshade Foundation started as a group of primarily aerospace engineers who were looking at the concept of how could space help. We have this is our napkin diagram. I just want to offer this for further context for how we see our work. We're all familiar with the reduce and remove and reflect curves. But we see the planetary sunshade because of its scale and because of its size as something that is a farther time horizon out than, say, hypothetical SAI deployment. But we also see it as very complementary to an SAI deployment. We there are two ways to globally affect the Earth's sunlight reflection. One is SAI, and one is a space-based sunshade. We think that they are very complementary to each other, and so we don't see ourselves as competing. As you all know, these are the ways to reflect sunlight, and we're going to spend the next 20 minutes talking about space-based sunshades. So we tend to frame our questions around this very big principle: what does the Earth want? What is the ideal climate intervention scenario? And then from an engineering perspective, seek to answer, well, what could space contribute? And I'll show you this in a second, but some of the capabilities that space-based reflection has could offer unique and different interventions and different climate results than what has previously been studied with SAI. Now, whether or not those are desirable is part of this exploration that we're doing, but we think it should be looked at. We are currently funded by the UK's ARIA program, and the Space Reflector Baseline Survey, which is our primary focus right now, aims to develop and compare various SRM options, and then work with the climate modeling team, including both Cornell and NCAR, to model as close as we can to actual engineering implementations. So we're taking it out of a hypothetical and moving it into what could these specific proposals do. And at the end of our project, which is just a one-year grant, we're going to be proposing a space-based experiment. We'll be delivering a set of modeled results based on the different space interventions, and establish a way for the sunshade community to talk about various interventions in an apples-to-apples comparison that has so far not been the case. So our work focuses on 6 different architectures, 6 different kind of representative types of ways that sunlight reflection could happen from space. And I'll go through these briefly here, and then we'll get into a little more detail on a few of them. So what we call architecture A is the most basic, the solar dimming model of a sunshade is also almost a one-to-one analog to the GeoMIPS G1 solar dimming experiment. It is the closest we can get to simply reducing the solar constant by 0.5%, 1%, etc. And that would be achieved by a fleet, not a single large mirror, but a fleet of spacecraft orbiting the Sun Earth Lagrange 1 point. We think that there has been some work done on this concept of an architecture B, which is the notion that you could have spacecraft orbiting that Lagrange point to cast hemispherically preferential shading. And we think there might be climate benefits to that. And so it's part of what we're looking at. We'll get into that and more in a second. Architecture C is looking at advanced materials to say that by diffracting sunlight slightly as opposed to reflecting it, you actually have engineering advantages in some ways for the construction and maintenance and operation of the sails. Architecture D is in some ways the most far out from a modeling perspective, because this is supposing that we could use materials that are selectively reflective, meaning that some wavelengths of light would be permitted to pass through and hit the Earth, while other wavelengths would be reflected back. This is the most unknown question, and this is where we're really relying on kind of early model results to tell us whether or not anything in that field of inquiry is even worth looking at. And then, of course, see if the engineering can conceivably construct something that could meet that. But at a conceptual level, it seems plausible, and so it's part of our effort. Architecture E that we study is this notion of a dust cloud, a cloud of particles around this location, instead of an engineered constellation of spacecraft. The advantages of this would be that it would be could be a lighter overall intervention. It could be easier to construct, easier to deploy. The disadvantages is that that location in space is not perfectly stable, and so those particles need some form of position keeping. We have some ideas that we're looking into. And then concept F is an idea that's been looked at and rejected a few times, and it is looking like that we will also be looking at this and rejecting this, but it's the notion of a low Earth orbit configuration. And some of the obvious downsides to that would be the collisions with other spacecraft in orbit, orbital debris. But even aside from that, the types of shading that you could achieve with a low Earth orbit constellation are actually quite limited, and we think would be more disruptive than helpful. And so this is our project. So let me get into a little bit more about what these actually entail. So again, big picture, conceptual level, the concept is very simple. Many people have come up with this independently. Many people will continue to come up with this. It is that if there were reflectors in space, that not as much of the sunlight would reach Earth, and you could achieve kind of an SRM result. Now, there's some constraints on that, and some important constraints that we think it's helpful for everyone to understand. So the location matters quite a bit. Everything in space has to do with gravity and momentum, and the Sun-Earth Lagrange 1 point is a point of gravitational equilibrium between the sun and the Earth. It's about 5 times further away than the moon, although it's only 1% of the way to the sun. And this point is determined by 4 forces, right? So there's a force of the sun's gravity, the force of the Earth's gravity. There's the centrifugal force of anything that's orbiting. And then there's the force of solar radiation pressure. And when these 4 forces equal 0, we get our free body equilibrium of not just the Sun-Earth Lagrange 1 point, but the Sun-Earth Lagrange 1 prime, we call it, which is up to 50% closer to the sun than the SEL1 point. That's to offset the solar radiation pressure. Solar radiation pressure is the force of photons, which have momentum but not mass. But when photons strike any object, they transfer that momentum into that object. And that force has been measured and demonstrated. It's the force behind the concept of solar sailing. The world has flown about 6 solar sailing missions to demonstrate that that force can in fact be used as a propulsive force, just like a sail on a sailboat. And that can be used to propel a spacecraft. It can be also used to make navigational course corrections to a spacecraft. And so a sunshade is necessarily a solar sail, right? It's sort of unavoidably a solar sail. And the amount of pressure on that solar sail then needs to find the equilibrium point with the other forces here at the SEL1 point. And so when we talk about sunshades, we are talking about a very specific region of space and very specific dynamic. Now, the one factor we can control on this is kappa, and I'll come back to that in a second, which determines how much pressure there actually is. But so from that SEL1 point or SEL1 prime, I want to emphasize this. It is far away from the Earth, and because it is far away from the Earth, any object placed there is going to cast a diffuse shadow. It's going to cast a penumbra on the Earth, which is contrasted and distinct from an umbra. An umbra would be a perfectly dark spot, like a full totality of a solar eclipse. That is not what we're talking about, and that would be impossible to achieve unless your sunshade was actually larger than the diameter of the sun. From that perspective. So instead, what you have is a fleet of sailcraft that are each casting a diffuse shadow, and that's what leads to the near perfectly even distribution of shade across the Earth from this point. And that is by definition, that is sort of unavoidable in this concept. Now, as you all know, when we look at uniform solar dimming in climate models, there's near unanimous consensus that the temperature differential on the surface of the planet is not uniform, right? We get an overcooling at the equator and an undercooling, particularly in the northern polar regions. And so a few people before us have asked, is there a way that sunshades could address this? And previous literature has suggested that there is. We're advancing that concept by placing the shadecraft above or below the ecliptic, the sun-Earth line. We sort of wasting shade, right? So you would need a larger constellation because you're not getting as much shade from each craft, but that you could have the penumbra triangle preferentially shading, say, the northern hemisphere, the northern polar regions, and the northern summer, and you could have those spacecraft orbiting that point on a 12-month oscillation, for example. Or you actually could have them maintaining position here and simply turning on and off during the seasons. And so we think that this architecture B, we think that we could achieve that preferential shading. And this is some early results, which on the right, we're now imagining that region of the Sun-Earth Lagrange 1 prime space. And we're arranging our spacecraft not in a single cluster around that Sun-Earth line, but this is kind of the most extreme example where we, in this case, randomly distributed, although in a real-world deployment, you would not have them overlapping each other and wasting shade. But you could achieve, this is a shade plot, so the blue areas are the areas with more shade or cooler. And so this is part of what we are going to be modeling with NCAR, and it's proving to be an interesting challenge to take an actual map of a latitude-dependent shade and put that into the model. So I want to go next into some of the engineering work that we're advancing, because our question is really, is it possible? Like, what would it take to build this? And the design task that we set ourselves this summer was to imagine imagine an engineered structure for a sunshade that was intending to maximize the amount of lunar-based materials and minimize the amount of Earth-launched material. Because a sunshade is typically discounted, it's typically not included in SRM literature and research because it's simply seen as too large and too expensive and therefore not feasible. And that very well may be true, and by most estimations that is, right? However, because of the scale involved, if there was a lunar industrial capacity to produce kind of simple industrial materials like aluminum foil, silicon cables, what could be designed? And so this design I'm going to walk you through a little bit is based on that premise. We know from Apollo lunar samples and other lunar return approximately what the mix of minerals are on the surface of the moon. It's approximately the same as the Earth. I think it's much less distributed. There's much less geologic activity. And we know that the highlands are different from the Mare regions, but both of those regions have a substantial amount of the aluminum that would be needed to create something like a sunshade, and glass cables can actually be spun from just a unmixed regolith. The way that we adjust the optical properties of a sunshade, a shadecraft, is by reducing the kappa. So kappa refers to the amount of reflectivity of a craft. Perfectly reflective mirror, for example, has a kappa of 1, and a material that, go to the next slide, it shows this a little better, and a material that emits all of the radiation out from the opposite end of the incoming sunlight has a very low kappa. And what that means is that the position of a sunshade constellation with a high kappa actually needs to be closer to the sun. And because it's closer to the sun, it necessarily needs to cover a larger area because the shade is having to travel further. The shade is more dispersed when it reaches the Earth. And so lowering the kappa is a way to have a smaller shadecraft and therefore a lower overall mass while still achieving the same shade result. And this diagram um, shows the sunshade mass decreasing across our different kappa lines and necessarily finding an equilibrium point with the mass and the distance to the Earth. And the lower the kappa is, the better that mass fraction is. And so part of our study focused on what type of lunar materials could be used to reduce kappa the most. We think that a titanium coating on the sun side with a aluminum foil as the main structure, and then allows uh, uh, to maximally diffuse infrared radiation on the Earth side of the sunshade, achieving a very low kappa. It's not 0.167. That is the theoretical maximum, but I think it's closer to kappa equals 0.48 here. The And so by this design, um, and so the other breakthrough that we had this summer is to realize that the structure of a spacecraft um, increases linearly with the size, or sorry, increases at a quadratic equation with the size, but the shade area only increases linearly. And we actually dug up a concept from the NASA archives. NASA did a bunch of research on this in the 70s to study, instead of a rigid structure, shadecraft, which has been the focus of all space-based sunshade research up to this point. We realized that by rotating a spacecraft, by spinning the spacecraft and using centrifugal force to maintain the rigid structure, that we achieve a far higher shade to mass ratio, and that insight alone lowers the hypothetical kind of engineered weight, the mass of a sunshade by as much as 1/3. And so that third is not enough to take us from infeasible to feasible by any stretch of the imagination, but it is the kind of insight that allows us to say that, well, this is far closer to something that we think is worth people spending time and attention on. And furthermore, if we look at the use of lunar resources, we are necessarily using far fewer launches from Earth. There's far fewer launch impacts to the atmosphere, and a far lower cost overall if most of those materials can come from the moon. This is so wrapping up last couple slides here. This is to demonstrate that this kind of area of the Sun-Earth Lagrange 1 prime point is actually a fairly large area of space. And we've done some work kind of placing, could these spacecraft fit in that area to achieve this result? And so on this particular design, some of the key numbers that we're talking about, this heliogyro craft is a 40-kilometer diameter design. That means you have 10-kilometer blades with 10-kilometer cables connected to a central hub. And the hub itself is the only part of the craft that would need to be launched from Earth, right? Everything else is really two components. The cables and the foil blades are designed with what we think are the abundant and likely lunar resources. And each shade would be 13 kilotons. Now, to achieve a 1% reduction in sunlight, that equates to about 4,800 of these shadecraft. So we're talking about a pretty massive fleet of craft. As I said, very high shading. 98% of the mass of the craft is directly shade material, so you have very little structural overhead. And this is designed to be, virtually 100% lunar mass. The total system under this configuration is 63 megatons. Very large structure. To put a reference point on it, we're talking something the size of the Three Gorges Dam in China is approximately 60 to 70 megatons of concrete. Um, Now, again, to emphasize the importance of lunar resources and the possibility of that, that would only be 21 kilotons of mass that would actually come from the Earth to directly build this, and that would entirely be the hubs, so the 5,000 hubs, and that equates to 220 launches of a Starship equivalent spacecraft. There's an asterisk here because that does not include any the launches that would be required to actually build lunar industry that could actually make this kind of thing, likely in the hundreds to low thousands more. We are in the process of publishing this work. We are, working with the solar sailing and space resources communities to refine these ideas. And ultimately, this is in service to the question of how could the world build a sunshade? Is it possible? Is it something that is even worth considering? So, to recap, the physics are well understood. The engineering and climate modeling are understood at the general and high level. Our work is refining the concept, bringing the numbers down, and really attacking the uncertainty. And I hopefully have described why lunar resources would be transformative. Happy to take any questions, and of course, love to keep in touch.
Thank you, Morgan. This is really cool. Okay, we already have a question from Mike. Mike, unmute yourself.
So very interesting. So have you thought about optimizing with respect to other than temperature? What if you were to try and do something to try and keep sea level rise down, so keep the ice on the continents, or do something to try and make sure AMOC doesn't collapse or promote its, I mean, which would again presumably be trying to preferentially cool high latitudes and letting the high latitudes pull the heat from the low latitudes instead of trying to directly cool all regions of the Earth by the same amount. Have you thought about various other optimization aspects?
Yeah, yeah, absolutely. I think this is the most direct response to that question is this idea that you could arrange the shadecraft in a way to preferentially shade the poles. Because of the distances involved, a shade or even a large constellation of shade at SEL1 is it's impossible to be so specific as to just shade, say, Greenland or just shade a single part of it. But from a kind of hemispherical level, from a general latitude level, yes, we think that the optimal configuration of the sunshade is likely has some latitude preferencing, similar to what the SEI deployments are looking at.
Thanks.
Yeah.
We have time for a few more questions. If there are none, I can ask a question. So, a concern when talking about stratospheric aerosol injection is the impact on health once the aerosols are gonna come back to the troposphere. So I was wondering if you have an idea what could be the impact on space pollution or tropospheric pollutions once, I don't know, these materials can come back to the Earth.
Great question. Um, I want to answer that in two parts. One is the both current and future launch and satellite industries. I I think that the number of launches that the Earth is currently doing, is approaching the level where you start to have very significant, not necessarily CO2 impacts, because the CO2, the greenhouse gas emissions from launch industry is a tiny, tiny fraction of the airline industry. But the we don't well understand the impact of putting emissions into the higher levels of the atmosphere, which is something that doesn't currently happen very much. And the impact of reentry of rockets actually has a heating effect, which can impact ozone in serious ways. And so the re-entry of spacecraft, which both puts, burns up and puts aluminum and other rare earth materials high into the atmosphere, and also the re-entry of reusable spacecraft through the ozone layer, have effects that I think need to be studied a lot more, and are frankly outside of the purview of our research, but is one of the reasons that pushes us toward really being curious about lunar resources, because lunar resources would be the difference between many tens of thousands of launches to build a sunshade versus low thousands. So that's the first part of your question, is that there are serious questions about the atmosphere, about spacecraft and space launches in general. Now, on the second part of your question, I actually want to draw a really sharp contrast, because the spacecraft, the Sunshade, remember that SEL-1 location, is 5 times further away than the moon. It's actually outside of the Earth's gravity well, right? So it's if you rolled downhill from SEL-1, you'd be rolling toward the sun and not toward the Earth. And that's a really key distinction, because most people don't think of this as being so far away from Earth and so far away from other in-space activities, but it really is. And when craft fail, right, they would fail kind of on that downhill side toward the sun. Um, so yeah, two distinct parts to your question. And I see Jeff Overbeek, our technical lead and my co-collaborator here. Maybe I'll just see if Jeff wants to add anything to that question, then we'll see if we can take Shuka.
Hi, everyone. Good morning. I'm really sorry that I missed the first part of this call. Glad to have caught the end. Morgan, I caught about the last 20 minutes. I think you did a fantastic job. Thanks for covering. And I think you answered that last question pretty well as well. Would you like me to add anything to that, Ilaria?
No, I think I got my answer. It was pretty clear.
All right. Happy to also answer any other questions.
Yeah, there is Shuka. Can I mute yourself?
Hi. A lot of fun to think about these things. Of course, it's very unfamiliar to most of us. I'm just wondering if you could orient us about the scale of solar winds that are variable and so on. Is that an issue at all?
Jeff, you want to take that one?
Sure. It's pretty much lost in the noise compared to nominal solar radiation pressure. Even if there was something like a Carrington event, I'm pretty sure that we can build and this is something that we just haven't gotten too far into yet in detailed design, but I'm pretty sure that we can build even avionics that can survive something like a Carrington event, which is really extreme. That's one in something like a couple hundred years. So for normal solar wind, everything will be secure for that and able to handle that.
Yeah, I was surprised by that the solar wind electromagnetic forces are orders of magnitude smaller than the solar radiation pressure. Um, so now we know.
It, because of where the sunshade location is, it'll be closer to the sun than anything that we currently have out there. And we'll actually be able to have earlier advance notice for any other satellites around the Earth, just by putting some sensors out by the sunshade system. And to even more so, we may want to move things more sunward from that to give the sunshade system some advance notice.
Okay, let's take this other question, the last one, and then if you have more question, I think you can email Jeff or Morgan. But please, Kevin, go ahead.
Yeah, am I on?
Yes.
Yes.
Yeah, you probably can't give a much of an accurate answer to this, but what about time scales? I mean, what's the best possible time scale for getting an effective cooling mechanism that, with space-based methods that you're proposing?
Jeff, you could take that one as well.
Sure. Okay, so I come from a background of very optimistic and aggressive aerospace system schedules. So the timelines that I talk about are that if we get serious about wanting to build a planetary sunshade, within 10 years we could start putting the first couple of sails out at SEL1 prime. And yeah, so it would take about 10 years to build up the infrastructure, both the lunar infrastructure to be able to export the materials to do that. And in parallel, we would start launching some from Earth, some of the preliminary sales. So it would take about 10 years before we get the first one, and then an additional 10 years to sort of exponentially build up production. And so, in other words, within 20 years, we would then have a high production rate and be at about 1 degree Kelvin temperature reduction, average global temp.
Okay, thank you. Okay, I would say that it's 9, so I mean it's 9 for me. I will end the meeting here. I want to thank again everyone, all the speakers and people joining this uh, meeting. We are gonna meet again probably in January, mid-January, because of Christmas time, AGU. So we will keep you posted with the next meeting. But yeah, it's gonna probably happen in January next year. Thank you, everyone, and see you soon.